All right, folks, let's talk about the two guided notes problems. We'll do level 3.0 first. That's this one right here. We have a complex circuit. As you can see, we have two parallelly connected resistors. The 100 and the 250 are connected in parallel, and the 350 and the 200 are connected in parallel. They together are connected in series. So it's this parallel packet connected in series with this parallel packet. To do this, we need to reduce it. Right, let's start by doing something easy. Let's take these two. They are connected in parallel. So if I want to find their equivalent resistance together, I can do 1 over 100 plus 1 over 250, and then do the inverse of that to get 71.4 ohms. I can do the same thing with the bottom packet, which is 1 over 350 plus 1 over 200 gives me 127.3. I'm then going to redraw the circuit, inputting the new equivalent resistors in the place of the parallel packets. So it's just a 71.4 in series with a 127.3. Now this is pretty simple. I just add the two of them together in series because series circuits add together, and I get a single resistor with a single battery. This is a reduced circuit. I highly recommend redrawing your circuit at every phase if you want to solve these correctly. It's the best way to do this. So effectively, these four resistors that we have at the beginning, 100, 250 in parallel, which are in series with a 300 and a 350 and a 200 in parallel, you could replace those four resistors with one 198.7 ohm resistor, and it would do the same thing to the battery. Now, if I want to solve for equivalent resistance, I've already done that. 198.7 is the equivalent resistance of this circuit. But if you want to start solving for the current or the voltage of a given resistor over here in the original circuit, what you have to do is work backwards. So we're going to start over here, and we're going to say on this side, well, this is a really easy circuit to solve for current. So I'm just going to say V equals IR. V is 24. R is the 198.7, and I can get an I of 0.12 amps. Now that 0.12 amps must be going through both of the series circuits on the second phase redraw of our original circuit, right? Because these two are in series, what they keep is current, because in series a current is the same. So if it's 0.12 amps here, it's going to be 0.12 amps there. Then I need to solve for the voltage drop of either resistor. So using V equals IR, for the top resistor, I'll say the current through the top is 0.12. The resistance of the top is there, and I can do the same thing for the bottom. Excuse me. The bottom is 0.12, same current, different resistance. So V top is 8.6. V bottom is 15.4. Let's do a quick check. How can we tell that that's right? Well, 8.6 plus 15.4, let's see, 0.6 plus 0.4 is 1. So I can add the 1 to the 8, which is 9, plus 15 is, hey, 24 volts. Yep, we're dropping all the voltage, which is what we expect. So we know that we've done this right. Now, when we go back to the parallel circuits, what stays the same in parallel? It's not current. Current splits between. The 1.2 amps is going to actually split between these two branches. But what stays the same is the voltage drop. So the top branch drops 8.6 volts, just like the 71.4 resistor drops 8.6. Either resistor will drop 8.6 volts because that's what parallel circuits do. For the 127.3, which drops 15.4, that means that each one of these is going to drop 15.4. Now, if you imagine yourself as a little electron, you go through and you say, oh, that's an 8.6 volt drop. Oh, that's a 15.4 volt drop. Oh, I've dropped 24 volts. Any path you take, 8.6, 15.4, or maybe a different way, 8.6, 15.4, you're always going to drop 24 volts. Now, to find the current in each of these, we have resistance and we have voltage, so I do I equals V over R, and I can say 8.6 over 100 and 8.6 over 250. Let's quickly just add these two up. 0.8086 plus 0.035 is, guess what? 0.12 amps. So we see that the current has split between these two. And then if I go down here, they rejoin to 1.12 amps here, and it re-splits. Let's find out how that works. We get the 15.4 over 350 is 0.44, and we get the 15.4 over 200 is 0.77, and when you add those two up, you get 0.12 amps. There's still that 0.12 amps in the circuit. It's just been split over two branches, dropping 15.4 volts. Here is the solution to every resistor. It's each resistor has an amount of current and amount of voltage drop. The 100 ohm is 8.6 volts with 0.086 amps. The 250 is 8.6 with 0.035, and so on and so forth. That's the solution to the 3.0. You guys ready for the 4.0? Tough one. This one is a multi-step redraw. Every single time you do something, you have to redraw the entire circuit. So this is how I recommend doing it. Start from the outside. Start with that 120. How is it connected? Well, it's connected to the 130 in parallel. Do you agree that these two are in parallel? All right, so let's just sum them up. And we can say, okay, 1 over 130 plus 1 over 120, and do 1 over all that, and I can turn it into a single resistor that I've redrawn. I've collapsed these two into just one of 62.4, which is the sum, the parallel sum of those two. But now these two are connected in series. So I can just add them up. 62.4 plus 140 is 202.4, and I can combine them. Again, I'm taking the two in series and just combining them with their equivalent resistance. But look, now that 202.4 is connected in parallel with the 150. So I'll add them up in parallel like this. I might point out at this point that you might have to pause this video occasionally to solve it yourself, but I'm doing it, sort of quickly. When I do the parallel sum of these two resistors, then I can redraw them as a single resistor of that sum, which is 86.2. But then that 86.2 is in series with the 170, so I just add them up and redraw. That's 256.2. That 256.2 is in parallel with the 160. Isn't this an evil problem? That's kind of awesome. So I take that 1 over 160 plus 1 over 256.2, and I can redraw them as a 98.5 and add it to the 110, and I get 208.5 ohms of resistance as my equivalent resistance. But oh no, we need to find out each individual resistor and its voltage and its current. So we need to go back up the chain. This one's really easy. I've just got V equals IR. I is V over R is 12 over 208.5. I'm getting about 0.058 amps. So that's the current going from the battery through the equivalent resistor. But this equivalent resistor really isn't that. Remember, if we go back up the chain, it was actually a parallel split between a 110 and a 98.5. Well, what stays the same? If I have a single resistor that's actually two parallel resistors, what stays the same? It's current. So I know that the voltage drop for each, the voltage drop for this is the current, the 0.058 times its own resistance, which is 6.33 volts, and that many amps. And then the other one is V, the same current times a different resistance gives me 5.67. How can I check? 6.33 plus 5.67 is 12. Now I've added these little voltage and current tags whenever we have an original series resistor, or an original circuit resistor. So that 110 was in the original circuit. The 98.5 isn't in the original circuit. The 98.5, if you recall, is actually a parallel split of a 160 and a 256.2. Well, what stays the same in parallel? It's voltage. So that 5.67 volts gets dropped by both branches. And then we just need to find current. Current is V over R. So I do 5.67 over 160 to get the current there. And I do 5.67 over 256 to get the current there. Again, I've added a little tag once I've found the permanent resistor. That's the one from the original circuit, so I'm going to add a little tag there. But this 256.2, it's not really a 256.2, is it? It's actually a split between a 170 and an 86.2. But what stays the same in series? It's going to be the current. So that 256 has 0.022 amps going through it, so I can use that to find the voltage of each branch. The 0.022 amps with the 170 ohm resistor gives me 3.76. And the 86.2 at 0.022 amps gives me 1.91. Now 1.91 plus 3.76 is, guess what? 5.67. So we know that we did this correctly because these two together are sharing the voltage dropped by the branch, which should be 5.67. Okay, now I've added a little tag to that 170, but the 86.2 wasn't actually an 86.2, was it? It was actually a 150 and a 202.4. So what stays the same in a parallel? It's the voltage, so that 1.9 volts stays true for both branches. So for the 150, I can say that the current is V over R. V is the 1.91 volts, and that gives me these two. It's a permanent, it's an original circuit resistor, so I'll keep the tag. And then that 202, let's see, it should get 1.91 over 202.4, which is this many amps. Notice that it's much less than the original 0.6 that we started with because it keeps branching out. So that 0.009 amps is going through the 202. But you guessed it, that 202 isn't really a 202. It's actually two resistors combined in series. What stays the same? It's the current. So I can say the 0.009 amps times the resistance gives me 1.32 volts. And the 62.4 with the same current gives me 0.59. Let's just double check. 0.59 plus 1.32 is, yep, 1.91 volts. But the 62.4 isn't really a 62.4. Oh no, it's actually in parallel. So these two, this is the original circuit, we're back. But these two are going to keep that 0.59 volts. And so I do 0.59 volts over 130 gives me this many amps. And the 0.59 volts over 120 gives me that many amps. And there is the solution. Notice that we have these little tags next to each resistor, the voltage and amperage of each circuit, each resistor in the circuit. I'll do it in the table that they gave you in the guided notes. There's the table, and I want to point something out really quickly. The sum of all voltage drops looks like it's more than 12 volts, right? 6 plus 5 is 11, plus 3 is 14, 15, 16, and change. We've got, it looks like we're dropping a bunch of voltage, but that's not actually true. Remember, an electron is going to go through maybe this one here, and then maybe this one over here, and this one over here, and this one over here. That's going to be a 12-volt drop. Let's even track it. 6.33, 1.99, that's about 8.2. And then we drop 3 more, that's 11 plus 0.8 is, 12 volts. There it is. So any one path that the electron take will be a 12-volt drop. But if you, there we go. If you try and add all these up, you're saying that the electron goes through all the resistors, but it can't do that. So the sum of the voltage is not 12, and likewise, the sum of the current is not 0.58. In fact, resistor 1 is already 0.058, and it splits in different ways and then recombines later. And then the equivalent resistance is not the sum of all resistors, and it's not the inverse sum of all resistors because it's neither series nor parallel. It's this funky combination of that, right? When we got back to the original, that's what the equivalent circuit is. But you can't just add up the branches and you can't just add up the voltages. It doesn't work like that. All right, there is your solution to 3.0 and 4.0 from the guided notes. More to come.